Alright, here we go. This is the very last video that we are going to do in RC/RL circuits. And this particular one is a parallel RC circuit with a faulted component in a multi-component branch. In this case, we are going to short around C3, and you can see that going up on your screen. Now, all the math that you see currently on the screen are the original numbers, so we're going to talk about how it's going to change. We're going to start with capacitance. Now, combining capacitors in series is actually a reciprocal formula. So the total of 2 nano and 7 nano would actually be less than 2 nano. But now, because we have shorted around C3, the total capacitance of branch 3 is C2, which is 2 nano. So capacitance is going up. And we know, because capacitive reactance is a reciprocal formula, that if capacitance is going up, then capacitive reactance is going down. Alright, so we're going to start with that basic knowledge, and then we're going to look at the math. We know that capacitor 1's ohmic value is not changing. Nothing on it has changed, so it's reasonable that it hasn't changed at all. It's the same with capacitor 2, so both of those will stay the same. Now we know that we've shorted around capacitor 3, so of course its ohmic value is going to go to 0. Okay, so now branch 3, which was 20.47K, is going to decrease to just the value of capacitor 2, which is 15.92K. We said that that was going to happen. Now, with a decreasing capacitive reactance in branch 2 and a capacitive reactance staying the same a decreasing capacitive reactance in branch 3 and a capacitive reactance staying the same in branch 2, we are expecting our total capacitive reactance to go down. And it does. It goes from 4.86K to 4.55K. Alright. Now, impedance is also going to change because even though R1 stayed the same, our capacitive reactance went down. So we are actually expecting impedance to go down as well. And it does. It goes down from 4.51K to 4.25K. Now, of course, if impedance went down, current must be going up. And if we look at those new numbers, we see we get 11.77 million. So it did go up, not by a whole lot, but it did go up. Now the current through branch 1 and branch 2, we're not expecting any differences there. They have the same voltage and the same ohmic value that they originally had, so they should still have the same current. The changes are happening in branch 3. So now with less ohmic value, right, branch 3 did have 20.47K ohms, and now it has 15.92K ohms. We are expecting it to have more current. And it does. It has 3.14 milliamps now. Now, if we put our current formula together, we put our new numbers in there, our new total current through our capacitors, we get something that is within just a couple hundredths of our total current of 11.77 milliamps. Alright, now voltage. Branch 1 and branch 2, R1 and C1, both still see 50 volts. But when we get out to branch 3 itself does have 50 volts applied to it. However, because capacitor 3 has no ohmic value, it doesn't matter what the current is or what the voltage applied is. Without an ohmic value, it will not have any potential difference. And so we will see 0 volts across capacitor 3. So if we were to put our black lead here on this side of our circuit and our red lead in between C2 and C3, we would see a total voltage of 0 volts because we are not, there's no ohmic value in between those two, so there's no potential difference. It's just a straight piece of wire. When we see no potential difference, remember our meter reads red minus black. If both leads read the same thing, it's going to take whatever that is minus whatever that is, and you will get 0 because both of them were the same. Alright, but capacitor 2 sees 50 volts. That is because, right, this potential on this side comes all the way to this side of capacitor 2, So if you put your reference actually anywhere down in here, and then you put your red lead anywhere up in here, you are reading across capacitor 2, and you would see your 50 volts applied voltage. So in this case, C2, capacitor 2 is 50 volts, and capacitor 3 is 0 volts. And that concludes our RC/RL video series. Like I said, next we are going to go into RCL circuits.